Let's start this lecture, Basic Concepts in Electromagnetism 2. It's lecture number 3, as you can see here. We'll do a quick review of lecture number 2 and then proceed with Basic Concepts for Electromagnetism 2. So the question for today, which all of you have answered, thank you very much, is what are time domain electromagnetic fields? What are frequency domain electromagnetic fields? And we'll answer that question during this lecture. And it's a very important concept in spectroscopy. It's a very important concept in how we can probe and look at biological tissues electromagnetically. So from the previous lecture, Basic Concepts in Electromagnetism, we will do a quick review of some of the basic concepts there and then proceed to the next lecture. So as mentioned, we had Maxwell's equations. The 4 equations are Gauss's law, Gauss's law for magnetism, the basic law for magnetism, Faraday's law, and Ampere's law. Gauss's law describes essentially the generation of an electric field from a charge. The Gauss's law for magnetism basically says that a magnetic field is not created from a magnetic monopole. It's basically not going to change from one within one surface or one volume. And Faraday's law states that a changing magnetic field will create a changing electric field, and Ampere's law states that a changing electric field or electric current will create a magnetic field. So we talked about quantized states of matter, Heisenberg uncertainty principle that describes the inverse relationship between momentum and position, as well as the inverse relationship between energy and time, which will be very important, as we'll see when we talk about time domain and frequency domain fields. But Heisenberg's uncertainty principle essentially states that multiple parameters cannot be simultaneously precisely determined in a quantum system. We talked about quantized energy levels as being the fundamental basis of spectroscopy, that energy levels for electrons have a ground state, and when we excite those electrons from energy coming in, we call that absorption, and that can be observed spectroscopically in an absorption spectrum. When those electrons also emit energy, that becomes a emission spectrum. So that was electromagnetism, again, very brief review. And we also talked about waves and the concept of a wave as a perturbation that spreads over space and time, because that perturbation influences the space and time next to that, and so on and so forth. This is the basis of mechanical waves, and those mechanical waves can also be described as transverse waves that are mathematically determined by trigonometric or sinusoidal equations. And these waves have 3 properties of amplitude, frequency, and phase shift. The frequency is inversely related to the wavelength. We also talked about the addition of waves occurring through a linear addition. 2 waves add up of same frequency, they add up their amplitudes, so that if they are of the same phase, they will add up constructively. If they are opposite phase, they will add up destructively, canceling each other out. So the wave total is equal to the additive sum of the component waves. Obviously, for waves of different frequencies, it gets a little more complex, but the same equation holds. So electromagnetic waves combines this concept of electromagnetism as determined by Maxwell's equations and the concept of waves, and we get electromagnetic waves as a reflection of a self-propagating perturbation through space of this interaction between magnetic fields and electric fields. And again, just like transverse waves, they will have an inverse relationship between the wavelength and the frequency, and a direct relationship between the energy and the frequency, as given by Planck's equation here. Visible light will be composed of different frequencies, again determined by this equation, whereby the high frequency or violet light corresponds to a low small wavelength, and the low frequency or reddish light corresponds to a large wavelength, or relatively large wavelength. And the general principles of the interaction of radiation with matter: transmission, where there's effectively no interaction; reflection, where essentially the light interacts with the matter and it is then reflected off that surface; refraction, when is a function of dispersion, where the frequency of the light or the velocity of the light will change, and thereby the direction of the energy will change as it goes through a medium. Diffraction is the constructive and destructive interference from a single point. Absorption is when that energy is absorbed and ultimately retransmitted in a different form. And scattering is when that object will then emit the light in many different directions, in 360 degrees. We can have several, basically fundamentally a photon is the electromagnetic radiation, and the electron is what is a part of the matter that is changed. The incident photon interacts with both core and valence electrons, so the photon can be absorbed, can be scattered elastically, in other words, with the same energy, or can be scattered inelastically with a different energy. And also the electron can be emitted, can be excited, or can be de-excited. So when we talk about the interaction of electromagnetic radiation with matter, we have both what happens to the photon and what happens to the matter as well. So these two principles are happening at the same time to varying degrees. We talked about reflection and diffraction, and these are examples of both. Dispersion is the change in the velocity, and refraction is the consequent change in the direction of the light through a medium, which changes that velocity. And the fundamental principle of spectroscopy, as I mentioned, is, of course, different spectroscopic experiments will be more complex, but this is the fundamental principle where you have a wide range of frequencies impinging upon a sample. You get an absorption spectrum where certain light is taken away from those frequencies, or an emission light spectrum where certain light frequencies are created. Examples of spectroscopy are where you have some emission of the particle, again, inelastic or elastic scattering, or electron emission, or no emitted particle where we have some photon being absorbed. So that's a quick review. Now let's talk about some basic concepts in electromagnetism 2, with time domain electromagnetic fields, frequency domain electromagnetic fields, conduction, polarization, magnetization, ionization, energy absorption, dosimetry, and a quick review of computational methods. So a very important principle in spectroscopy is the concept of a Fourier transform. A Fourier transform implies that any function, any type of pattern can be created as a sum of sinusoidal or trigonometric waves. So this is a sinusoidal wave is given in its exponential form, e to the minus I omega t. That is the exponential form of a sinusoidal wave. And that's because a sinusoidal wave is essentially a reflection on either the x-axis or the y-axis of a rotational motion. So it's a reflection on the real plane or the real axis of a complex number, and that's why we have a complex number here rotating. by a certain frequency omega. So this e to the minus I omega t is essentially a trigonometric wave function. So as this t goes from minus infinity to infinity, we sample different waves by a certain amplitude, again, frequency, amplitude, and we can create by adding up, namely an integral, by adding up all those waves of different amplitude, we can create any other function. And then we can go back from that function, the inverse transform, to get those frequencies, or those amplitudes, excuse me, by then multiplying that Fourier transform by the waves, by the component waves. So here's an example. Since the Fourier transform is a sum of waves to create a function, then if we want to create the Fourier transform of a single wave, that's only going to be a single number or a single frequency. In other words, that one frequency here. Another way to look at it is if we wanted to make one cosine wave as a sum of an infinite number of cosine waves, obviously all these other infinite cosine waves are going to have an amplitude of 0, and only one will have a non-zero amplitude. So this is the Fourier transform of a pure cosine or sine wave. If we have a signal that looks like this, we have a uniform band of frequencies over a certain space. A Gaussian turns out to be also a Gaussian, and a double exponential turns out to be a Lorentzian. We don't need to know the details of this, but basically there is a relationship between the signal and the Fourier transform. So the difference between time domain electromagnetic spectroscopy, frequency domain spectroscopy, is related to these different waveforms. So in the time domain, a sine wave is just going to be an extended sine wave. In the frequency domain, it will just be one frequency. If we have a very complex number or complex time domain that's a step function like this, the frequency domain will be a range of frequencies. So we have frequency domain and time domain. Another way to look at this is if we are doing a frequency domain measurement on a sample, then we are going to sample it at different frequencies, one by one. We call that a frequency domain measurement. If we're doing a time domain measurement, we can actually have many frequencies represented by a pulse. So for example, we go back to the previous slide and we see here several frequencies represented here by several frequencies by these pulses. So you do a pulse and you get several frequencies sampled at the same time. We call that a time domain experiment. So in MRI or NMR, as you know, which is used in medicine, we do a pulse of radio frequency radiation, which creates many different frequencies all at the same time. And that time domain experiment is a very powerful way to sample an object over many frequencies all at once. You don't just shine light of one frequency, you shine light or electromagnetic frequencies or energy of many frequencies. And so that's a time domain experiment versus a frequency domain experiment. So we talked about MRI, and the basic physics of MRI is a patient is placed in a magnet. That magnet will create differences between the magnetic spins in the hydrogen atoms or other atoms, mostly hydrogen in that patient. And the radio waves are then passed in pulses, and those pulses will excite many of these protons, and then the protons will relax, also emitting their radiation, and those radiation will be detected, again, radio waves, and transformed into two-dimensional images, T1 and T2. So we can see here the bone, the muscle, fat, and this is blood here. So actually a fluid mass. So we have different signals, high signal and low signal with T1 and T2 relaxation on MRI. So again, we create a static electromagnetic field that will excite or create a difference in energies among protons. Then these protons are excited by a pulse of radio waves. That proton relaxation is received. That's also Fourier transform, and that will then create a two-dimensional image on detectors that are also moving around or rotating around the patient to create a three-dimensional image. So one of the important principles in electromagnetic radiation is also how it fits with other ways of transmitting energy. So radiation is photons, as you know, but we also have conduction, which is heat energy directly being conducted through a material object. We have radiation, which is heat energy being emitted through infrared radiation. And we have convection, which is heat energy being moved by the physical movement of some material, a liquid or air. So in this case, we have electrical heater that is radiating heat. You can feel that as infrared radiation. It is also conducting heat into the pot. That, of course, goes through the handle as well. And then that heat is going to be transferred to the upper surface via convection, which is the physical flow through the material. These electromagnetic waves will have one direction that is a electric field changing, and the perpendicular direction with the magnetic field changing. And of course, that transverse wave is in 3 dimensions, so it can be in one direction. We call that linearly polarized light. Light that goes in all directions, rotating, is circularly polarized light. And unpolarized light is a light that is linearly polarized, but in all 360 degrees. So insects, as we'll talk about in a later lecture, can actually navigate from the sun and can navigate relative to the sun using polarized light. The electric vector orientation is also going to influence through their eyes certain cells that will be activated as a function of the orientation of the electromagnetic vector in polarized light. Ionization energy, as we mentioned, is pulling an electron away from an atom or molecule. And this is a very important principle, as we talked about with ionization, ionizing energy. Ionizing energy is energy in the X-ray or gamma ray region that can ionize atoms or molecules. In other words, pull electrons away to create an ion. And that is very damaging to tissues. It can be damaging to DNA. And there are 2 types of effects with ionizing radiation. One is the deterministic effects, and the second is the stochastic effects. Stochastic refers to probabilistic. Deterministic effects depend on a fairly high dose, And they also are dose dependent. They effects are pretty short term, so you have damage over a course of minutes to hours to days. There is a threshold dose. In other words, the body can repair radiation damage ionization up to a certain level. And the biology is actually cell death due to the radiation. The clinical effects are effects on the skin, redness, ulcers, loss of hair, cataracts in the eye lens, and also effects on the gastrointestinal tract and the bone marrow. The stochastic effects, namely by chance, can occur at a low dose. There is no definite threshold effect. Usually the occurrence is over a long time, and this is mediated not by actual damage to the cells, but by DNA damage. So the effects over time are genetic effects or cancer. These are different sorts of effects of the body, and the effect on DNA can occur either directly, direct ionization of the molecule of DNA, or indirect action, which is, as we talked about in the overview lecture, ionization of a water or some other oxygen-containing molecule that creates a hydroxide free radical, and that free radical can then create damage to DNA indirectly. So direct ionization of DNA or indirect ionization via free radical mobilization. So the absorption of energy by tissues, or absorption in general, is determined by the Beer-Lambert law, Beer's law, and it's specific for a substance and it's specific for a certain frequency, or wavelength. So this is the Beer-Lambert law, and it essentially states that the absorption is going to be a function of some intrinsic property of the material called the absorptivity, molar absorptivity. The concentration of that material and the path length, or how long it is going through. So if we have energy coming in, the absorptivity is going to be a function of the length. The intrinsic absorptivity, the absorption is going to be a function of the length, the intrinsic absorptivity, and the concentration of that. So as I mentioned, X-rays go through the body very easily, so their absorptivity of the body is very low. But there are some parts of the body, as I mentioned, calcium in bone and iron in blood, that actually have a high molar absorptivity, and they will be more absorbed. And of course, the length and size of that is going to determine the absorption. And so these characteristics relate to how X-rays, for example, or any radiation is absorbed. So an increased concentration of some material is going to increase the absorption. The increased length is going to increase the absorption. And of course, specific absorptivity related to that molecule or substance is also going to increase the absorptivity. We're approaching the latter part of the lecture. I wanted to review Gauss's law again. Gauss's law states that the net flux of electric field outside a certain area or enclosed by a certain volume is going to be proportional to the charge inside. We have an integral form, which is the most common form that Gauss's law has introduced, and we have a differential form, as you can see here. So computational methods of calculating the electric field around a charge distribution are going to either be differential equation solvers based on these differential form of these Gauss's law, roughly speaking. So there are method of finite differences, finite element method, and Monte Carlo methods. The other computational method will be integral equation solvers. So method of moments, boundary integral method, charge simulation method. Again, basically following the two different formulations of Maxwell's equations, either a differential form where we build everything up point by point and then calculate what the field should be, or an integral form. Most computational methods will use differential equation solvers. So I'll end with a closing thought for this lecture. This is Michael Faraday. He was a collaborator with, he was one of the fundamental early experimenters with electricity and magnetism for the Royal Society. And he has a quote, "I happen to have discovered a direct relation between magnetism and light, also electricity and light, and the field it opens is so large and I think rich." And indeed, this interaction, this connection between electromagnetism and light is very important. And as we are developing and continuing in this course, the interaction of electromagnetism with matter opens up a huge field with as much possibilities as I'm sure Michael Faraday imagined. So the next lecture will be next week, lecture number 4. So we are going to catch up step by step. Will be basic concepts in biology. So we basically did very basic concepts in electromagnetism, just so we have a common vocabulary, some basic principles. We'll then do one lecture about basic concepts in biology, and then we'll start to bring those two together. Those are the principles of bioelectromagnetics. And as I mentioned, the latter part, the second half of the course, will be the applications of bioelectromagnetics. So the question for next week, which I know all of you have answered, what is life? And we will try to answer that question next week. So that's the end of this lecture. Any questions? You can type into the chat room.